question number 18, we have a figure 39E1, and it shows a typical circuit for a low pass filter. What is a low pass filter? This is a voltage of sinusoidal voltage, and in this problem we are given that an AC input, AC means alternating input with some frequency with input voltage at 10 millivolt, is applied to the left, and we are observing the output voltage V0 at the right hand side. We need to find the output voltage for V equal for frequency 10 kilohertz, 100 kilohertz, 1 megahertz, and then 10 megahertz. And we need to observe that as the frequencies increase, the output decreases. Let us understand it a little bit, this problem. Let us say instead of this capacitor, there is a resistor here. So if we connect a resistor, something like this, and this is a input voltage, an AC volt, or for that matter DC volt. This is R1, this is R2, and this we are given 1 kilo ohm. If this one is 1 kilo ohm, then half of this voltage will appear here. Let's say this is how much given, 10 millivolt, and this is also 1K. This is also the output will be 5 millivolt. If this resistance we change to lower impedance, for example, instead of 1 kilo ohm, let us say I connect this 1K here, and then this is maybe 100 ohm. Then the voltage at here will be 10 millivolt multiplied by 10, 100 ohm divided by 1.1 kilo ohm, sum of these two. So this has reduced, so this voltage will be much less. It will be about maybe instead of 5 millivolt, about 1 millivolt. If I reduce it even more, then it keeps the output voltage keeps giving on. The reason I wanted to give this background is, let us consider this case where this is 1.0 kilo ohm, and we have a capacitor, and then the impedance of this capacitor is given by 1 upon 2 pi f into C. As we increase the f, Z decreases. When Z increases, the output voltage V decreases. In other words, this is frequency and this is our output voltage V. Then as we increase the frequency, the output voltage decreases. And that is why we call it a low pass. What is mean? Low pass means the low is passed. It passes the lower frequency, but it cuts the higher frequency. And that is the whole idea of low pass filter. This is the qualitative analysis of this problem, and now we are going to solve this problem. So come back to this. What we are going to do is, first we find the current in this circuit. The current in this circuit I will be given by V0 divided by Z, and now we have found the current to the circuit. The voltage across this V0 will be this current flowing multiplied by the impedance of this capacitor. So the voltage out, this let's call it VE, VI. V out will be equal to I multiplied by XC, where XC is the impedance of this capacitor. VI divided by G, and XC is given by 1 upon 2 pi F into C. And this we can write as VI. And now Z is square root of R square plus 1 upon 2 pi F into C whole square, and this whole thing multiplied by 2 pi F into C. What we will do is VI divided by, if we multiply this one here, this thing and this thing will cancel when it comes out of the square root. So we will get square root of R square, and then 2 pi FC whole square becomes 2 pi FC whole into R whole square plus 1. This is the output voltage. Now as F increases, voltage decreases. And let us calculate it for different values of f. When f is equal to, the first thing we are given is f is equal to, right here, 10 kilohertz. Let's keep f is equal to 10 kilohertz. So Vi is 10 millivolt divided by 2 into pi 3.14. F is 10 kilohertz, so 10 to the 10 into 10 power 3 multiplied by C. Capacitance is 10 nanofarad. 10 into 10 to the power minus 9 nanofarad, and R is 1 kilo ohm. So it is 10 to the power 3 whole square plus 1, and then you will take a square root of this whole thing. So 3 plus 1 4 plus 3 7 plus 1 8, and this is 1. This is 10 to the power minus 1. So this becomes 10 millivolt divided by square root of 3 into C 0.6, and this is 6 multiplied by 0.1, this is 0.6, and this whole thing, and then this is plus 1, 0.6 plus 1. This will be 10 millivolt divided by square root of 1.6. And if you try 1.3, this will roughly equal to 8 point. I'm looking at my answer in the here. You can do your calculation, 8.5 millivolt. Now you increase this frequency. This is at f equal to 10 kilohertz. If you increase it further to f, to say the next thing 100 kilohertz, it is 10 times. So what will happen? F is equal to 10 millivolt. So this square root of this 1 stays constant, and then plus this whole thing is square. So we had what we had this 6.6 square. Okay, this is 0.6 square, so this is actually 1.36, and square root of 1.36 will be something less than 1.3 and something like that. So anyway, this is 0.6 instead of 0.6. We will have 6 square. So this is 1 plus 36. So this will become 10 millivolt divided by square root of 37. This will roughly should be equal to 10 millivolt divided by 6 point something. Let us try to see if our answer is correct to this answer. So this is 1.6. So this is very close to what we got. 6 1 times 6, 40, 1.6 millivolt. And then this is 1, 2. In the third case, we need to find it at 1 megahertz. In 1 megahertz, this will become 10 millivolt divided by square root of, instead of 6 became 0.6 becomes 6. Now it will become 60. 60 square will be 3600 plus 1. This will roughly be equal to 10 millivolt divided by 60, or roughly equal to point what is that, 0.16 millivolt. And finally, once you go to, in the same way you can calculate it at 10 megahertz. So this will be 0.016 millivolt, 1016 millivolt, which you can write it as 0.116 microampere. So this is the whole thing. The key thing is that as the frequency increases, the impedance of this capacitor decreases and the output voltage goes on decreasing, and that's how it is working as a low pass filter.